dozens of cover letters a week, and I'm telling you, if you want to get, that's an important skill to have, right? To be able to get people to read your email, because it's really easy to ignore email. There's definitely an art to it now, like what you put in the subject line, what you start off with, how to just the right amount of content without overwhelming people. So I could talk to you for a whole hour about that, but instead we'll talk about semiconductors. So let's see, homework is in here. I have any burning issues on this homework? I have the key, yeah.
Oh, well, you're going to post the key on the email. It's about the homework, but when you change the Fermi energy, does the band gap change or does it stabilize? Because if you're doping, it goes to
of
the
course.
conduction band.
Yeah,
if I got the same result, so that doesn't make sense.
Same result as
the non-doped.
Which question was this?
It was question 1. Or I mean 2.
So there you're looking at the probability of a state being filled.
They're both the same probability.
Of doped versus non-doped?
Which doesn't make sense.
So you just started inventing a doping situation? Because there was no doping.
Part B.
Oh, part B.
Part B, yeah.
Yeah. What do you got the same number for A and B?
Yeah.
You shouldn't have.
Yeah, that's what I was thinking. So
No.
I changed the conduction energy, but not the band gap. Is that not how you do it?
Well, what you do there is the recognition that E term
Goes to 0. Oh, I see what you're saying.
right? So if these two equal each other, then this is E to the 0, which then is 2.7. The KTs end up canceling.
Yes, I got it.
What's that? Let me. Let's do it over.
Calculating E based on the expression that you gave us in the question.
I'm telling you this, so you have two things going on here, right? In this expression, right? I told you E of interest is E conduction band plus KT, right? Now, what is this? How did I phrase the question? I phrased the question such that it's the Fermi energy, right? Equals EF, which equals EG over 2, right?
Yeah, in the first case.
In the first case, yeah. So therefore, you can just put these into there. Now, what if
Mu equal EC, right?
if mu equals EC, then you have E to the EC plus KT minus EC, and then remember that's over KT, right? So then that's EKT over KT, right? Which I lied to you. It's not E to the 0, it's E to the 1. Yep. So the full thing then is 1 over E to the 1 plus 1. And I think it comes out to 0.2 something. Yeah. Okay. So another good question that came at the end of last class was this. So remember, let me pull up our visual. So when we derived those expressions, we used this kind of K-space diagram. And so since K is frequencies, these axes represent energies, right? And we said that in this situation, n pi over L, we have a unique solution, a boundary condition where it goes to 0. And so we can start to define these individual quantum states at each of these conditions in K, X, Y, and Z. Okay? And then we we did look at the number of states, okay? Where we looked at the volume of 1/8 of this sphere, 1/8 because we only looked at positive frequencies, And we divided the volume of that sphere divided by the volume of one of these cubes, one of these individual states, okay? And we did that to get the number of states, right? Then we went and looked at the density of states, which is the number of states per energy per volume. And then I brought in this volume term again, okay? And the question was here, I thought we already dealt with volume up here when we looked at the volume of the sphere, right? But the volume here, which we said is L cubed, is now in a spatial dimension. L is, in this case, is not a frequency dimension, right? So the first volume we were looking at as an energy term, and L now here is a physical dimension. So you could be asked, and I think I have an example today, where you have a 100 by 100 by 100 nanometer piece of silicon. How many states are in it? Which would be more than a smaller piece of silica, right? Yeah.
We're going to have further homework problems to practice that kind of concept on before too.
I think I have one more in there. Yeah. And we'll do one today. So summarizing again last time, yes, we looked at this. We looked at how there's these different dependencies depending on how confined a system is. This was in the notes from last time. This was a homework question, and I don't think we had quite gotten it that far, but it was in the notes, because what this is now asking is for the effective density of states, okay? And what that means is if we have our density of states, and which is per energy per volume, and then I multiply it by some energy. So now I have the number of states per volume, right? And so that's why here in this 3D system, our energy term goes to the 3/2, because it was to the 1/2. Yeah.
Wait, so...
This is a totally different equation than what we derived.
Oh, okay.
So this was on, I hope I posted this. If I didn't post it, that's shady. But I'll post lecture 13 today for sure, so if lecture 12 is not posted.
Snuck into lecture 12, but it wasn't really explained.
Okay, so yeah, what we did was we derived all of these, right? This was the one we spent the most time on. We got as far as here for a 2D system, and then I'm going to make you do a 1D system on the next homework. Now, what's kind of confusing is where does this term come from right here, okay? Well, there's many of things that are confusing. So let's walk. You would be given this on an exam. You would have this table, so we should talk about it. Let's just stick with the 3D system for now. So here, this was the equation that we derived. We looked at it through two different ways, right? We looked at it both as H and H bar. So if this looks weird to you, in the notes, it's written as both ways, just H and H bar. And so here is our delta E, which you can consider as the energy above the conduction band, okay? Or at any given point, if we're looking at energy, density of states, and it goes like that, we could say at this point, what is our density of states per energy?
So in this case, our EC would be the bottom of the...
Yes, which would be 0.
Okay.
Yeah. Yes. So when we derived it, we just condensed this as E, just plain E. So the example we're going to do next, EC is going to be 0. Yeah. Effective density of states, number of states times multiply the density by the energy, okay? This additional KT term. And that's where this comes. So this is the exact same expression multiplied by KT, okay?
I notice energy is not showing up in our effective density of states. Why is that?
No, it's there. Now our KT is to the 3/2 term. So here we have energy to the 1/2 term, and now it's to the 3/2.
But isn't E our variable input in the second column here? We don't really have a clear input here in the third column.
Sure you do, it's temperature. Yeah. Yeah, so this was how would this change as a function of temperature, which would in turn then look at your energy. Okay? This we derived, this m over pi h bar squared. And we said, wow, that's interesting that that's a constant. And we looked at it like this, right, as a step function. But a lot of times this community will also plot it like this. So what that's just saying is that the density is constant until the next allowed state. So if we were looking at a quantum dot made of, like sodium that has one valence electron, the density of states is going to be constant for that, well, not 1s, well, not 1s as in 1s, meaning a s electron, right? So we can look at all of the densities for that s electron. But then at some point, if we put in enough energy, we can start to do conductivity, or semiconductivity on the next energy level below that for a small piece of sodium, right? And so that's what this represents. Okay? That's why that's a step function. And same thing with a 1D system, right? You should have two states, conduction or valence, right? And here it's kind of written as multiple states for a quantum dot system. And that's why this is written here as this kind of step function. But if you did the number of density states, because here you're multiplying it by any given energy, goes to 2. Yeah.
So just to clarify, our delta here stands for the Dirac delta function?
Yes. That's exactly what it stands for, yes.
When you multiply KT by like that Dirac expression, is that what it goes to, or is it for a reason? You're
saying here?
Yes.
Yeah, because this is at a given energy. You're saying why does this go from here to here?
Yes.
Because this is considering only one of these states. Right?
Okay.
Yeah. Whereas the density, the middle, the one in the middle is considering this entire area. Whereas the effective density of states would be looking here. 1, 2, or 3. Not at all three of them.
So what is that mathematical result of 2? We have a constant 2. That seems unusual. And we could have different densities at different energy levels.
It's awful. What does this mean?
Yeah.
This means that you have only 2 states, conduction band or valence band. 1 in each. Right? That's it. Up or down. Okay. Okay. So here again, there's no, in the absence of this Dirac function, right, there's no energy term here. And so now when we multiply it by energy, it's just e to the there's no power term, e to the first power, right? Okay. Okay, so could we do this? Calculate the number of states per unit energy in a 100 by 100 by 10 nanometer piece of silicon that has an effective mass. We talked about effective mass. Remembered that when we consider these electrons in this lattice, that they have a slightly different mass than what they would unperturbed. For example, the mass of an electron in an atom of silica is going to actually behave different than in a lattice of silica because there's a lot more protons affecting it, a lot more other electrons affecting it, yeah.
Is that because of like relativity, like they're moving very fast, or is that
my understanding is that it's just because of for a couple things. One, because of the delocalized wave functions as all of those individual wave functions overlap, and 2 is because it's experiencing many more protons, right? So here it's actually slightly heavier. So it's 8% heavier because of all the other electrons that are around, or protons that are around it. It's my understanding. Okay. 100 millielectron volts above the conduction band edge right? They result in units of electron volts. So here you want to read these problems carefully. It's saying number of states per unit energy. Okay. And it's giving you a volume, so that's kind of a clue. If it was saying effective density of states or total states, you would want to look over here. But it's not. It's the number of states per unit energy, right, which is kind of our definition of a density of states, right? But it's throwing in this volume. Okay, so one thing you might say is, well, which equation do we use? Right? Is this, how small is small, right? Is this a quantum well? Is this a quantum dot? And I can tell you that in this situation, we can consider this to be a 3D system, still a 3D system, right? The only thing that we would possibly get close to is, is this 10 nanometer is the only thing that starts to approach quantum confinement. But for these 2D systems, it's generally like a single layer of graphene is a 2D confined system. Okay. So we're starting out with this expression, right? So okay, life's good thus far, right? We're just putting these in. This is H bar, not H. Okay. Now, what to do about that E term? So here, because it's above the conduction band, so we're considering that EC to be 0. So we're just going to look at 0.1 EV. Unfortunately, this is in units of joules. So what we're going to do is 0.1 times 1.60 times 10 to the negative 19th joules. Because that's our relationship. Okay, so here I get 0.051. This a big number. And this thing is 1.26 times 10.
Professor?
Yeah.
Using the 1.6 times 10 to the negative 19, because that's joules per electron volt, right?
That's right. Yep, this is our conversion from EV to joules because our Planck's is in joules. We could have just as easily looked up Planck's constant as an EV, right? Could have totally done that. Yeah.
Can you just explain one more time why the E minus E sub C is just the 100 millielectron volt?
Because we're considering here the conduction band to be no energy, zero energy, right? This kind of like how we derived it here, we're just calling it just plain E. I can't imagine a situation, at least for this class, where you'd be asked to like be given two different numbers there. Yeah. What is a different situation? I mean, you could imagine a situation where Like if I said between 5 and, yeah, I mean, that would be a reasonable question. If I said calculate the number of states between 5 and 6 EV, and I could say, you know, assume it's flat out here so you wouldn't need to use calculus. Or yeah, you wouldn't need to integrate it. You could just assume that this is flat. So then you would look at the difference. So then this would become 1 EV, right? But what does your other energy term then become? If we're multiplying it, then you would use your other, like either your KT term to fill that in, right?
Yeah, the one on the board, right?
Yeah. Yeah.
Oh, sorry. Why did you multiply square root 0.1 and joules? Sorry.
This one?
No, the one on the right.
Oh, this term? This is just converting. So we're given 100 milli-electron volts equals 0.1 electron volts, and 1 electron volt is 1.60 times 10 to the negative 19th joules. So this is just converting from electron volts to joules here so that it matches our Planck's constant term. Okay, yeah. Nope. I would just look at what the question, how it phrases it. Yeah, yeah.
Shouldn't there be a KT term in this equation instead of just what was given, since that was the conduction band was like, why did you assume it was 0?
How did I phrase it? How is it phrased?
Oh, so the difference is already equal to 100, so you don't.
Yeah. Yeah.
And to clarify what you're saying over here about adding the KT, since we're looking at the total density between 5 and 6 electron volts, why can't we just say our delta E is just 1? Why?
Oh, it is. Yeah, the delta is 1.
So where does KT?
Yeah. So now, but then you want to know the, yeah, it's actually, KT is probably not the best expression. Maybe you would want to use actually like 5.5. How would you use it? So this would be, you would calculate your density of states in this situation. So here, this would become 1 EV. Then you would multiply it by 5.5 EV to cancel out that.
Geometrically?
Yeah. Yes. Yes.
So, okay, geometrically looking at this then, 5.5 is the height.
Is the approximate energy where these density of states are occurring.
How did you know that? Is it just like
because it's posed. It's like it's looking specifically between 6 and 5, right?
So on that graph, what does our solution to using the 1 for energy represent? Is that our height? It doesn't seem.
No, it's our width.
Right, the 1 is from our width, but when we plug that into our density equation, the output of that density equation, does that reflect on our graph geometrically? Is that represented geometrically somehow? Because we're talking about the area of a rectangle effectively, right?
Wait, let's start this one over. Let's say, yeah. Okay, so let's say, I think I actually have this one written down. Are we good on this one? Well, let's finish this first. Okay, so you're looking at this piece of silica. Now we have this result as 1.53 times 10 to the 46th per joule meter squared. Okay, and then the only thing that we have to do is multiply by volume, right? And if you do it, it's 1.10 times 10 to the negative 22nd meters squared. And then if you again convert to electron volts, per electron volt. So a factor of 19 here roughly. Okay, so if you had a bigger volume, you'd have more states. Smaller volume, less states. Okay, let's just briefly do this one. So if I said you have a generic piece of metal, how many states? How would it be phrased? The number of states. If I gave you like it's 1.23 centimeters squared between 5 and 6 electron volts. Okay, so first you would use your
Professor, here we're looking for effective DOS or number per unit energy.
How do you want to do it?
Why not both?
No, so if you're doing,
Assuming that 0 is the edge of the conductor there?
yeah, so let's just do total number of states, period. If I'm giving you volume, right? So you can even take this one step further, right? If you multiply this also by volume, then you're just down to states, period, right? Here we're doing density of states, which is per energy per volume. Here I'm multiplying it by energy. What if I take it one step further, multiply it by volume? Which is kind of what we did there, except that we didn't multiply it by energy. We looked at, we're still left with effective density of states, number of states per energy.
So over there, we did the middle column?
That's right, for a known volume.
Okay.
Yep. And if you look at how that question was phrased, calculate the number of states per unit energy. So what if I said here, calculate total number of states? Okay. So here, what I would do is I would first, to know what's our density at this point, our density, I got on the wrong track earlier, so listen to what I'm saying now. This is 5 and this is 6. So here you would take 5.5 EV, which is, we're going to assume that this is asymptotic up here, so this is roughly flat. And then I would put that in here. Okay, because that is our density in this region. Okay? So this, when I solved this, it's going to give me a value of X states in units of, let's just say it's per EV per meters cubed. Okay? Then I would come through and multiply by my difference. 1 EV, and then I would multiply by 1.2 centimeters squared. Yes, this is right. Yes?
I want to understand your logic behind why you chose that number specifically.
Which number?
The 5.5.
Because it's equidistant between these two, and we're assuming that this is asymptotic, and so that the density is changing very little in this point. So we can just have it be the average, right? Right? First we want to calculate what's our rough density of states in this region. And then over this difference between these two regions. Okay, so this is telling us our density, and then I'm looking at this region. Yeah.
Why are you choosing between 5 and 6?
You could pick any number.
Wait, so is that calm related?
No,
They're different?
different. Sorry. Hold on. Yeah.
So the 5.5 is what's going to go into the square root of the difference in energy
Yep.
in the second equation?
Yep.
And if we were to want to find the number of states for the same first example that we did, is there any way we could use
It would depend how the question would be phrased. So if it would be phrased from 0.1 electron volts above the conduction band to 0.2 electron volts above the conduction band for a 1.2 centimeter squared piece of, then we could do the same thing in this example. Yeah. Yeah.
This is like my second least favorite question ever, but what is the engineering significance of the number of states?
What's your first?
Will this be on the exam?
Oh, yeah. So if you wanted to choose a material, well, maybe if for a nano perspective, if you wanted to adjust the density of states such that you can control the location of fluorescence, or the ability of a material to conduct electrons, right? So if it has more states, what do you think's going to be a better conductor? More states or less states? More states, right? So here, this will help you engineer a material to have the right conductivity that you desire, right? Yeah.
So for that problem, we were finding states per energy, right?
Yep.
And for this problem, we were just finding numbers.
Total number of states. And that's what we did. Well, first we calculated the number of states, and then we multiplied it by our delta E and our volume. Yep. Yeah.
This kind of like side related to like the doping. Would you just like take a piece of metal and like drop it into like a lower high pH solution to either get like holes or electrons?
How do you physically do doping?
Yeah. Just like drop it in.
I think it's when it starts in the solution phase. I don't think you actually like drop it in.
Plasma at 2 to like boron and phosphorus and those.
If you have silicon, then you like put something with one more electron and one less electron, and then you shoot like the atoms at it until it just like diffuses it.
Sorry.
See what they do.
I've never done any semiconductor stuff experimentally. Okay, so let's go on and talk a little bit more about when exactly do we start to hit these situations? That was a question that came out of last exam, is like when does nano become nano? And so remember this briefly, that when we multiply the density of states by the probability, we can start to get these carrier concentrations. And I'm going to skip through this quickly because I want to cover the rest of what we get. This will be on the notes, but here this is mathematically, where we multiply the probability distribution times the density of states, and if we integrate from 0 to infinity at 0k, then we can solve for the number of free electrons per unit volume here. Okay? So what's kind of interesting here is that n is the number of electrons, and it only depends on the Fermi energy. And vice versa, Fermi energy only depends on the number of free electrons. And we can think about this as the number of free electrons per unit volume. Okay? So the point is that the number of free electrons starts to become a very important descriptor and starts to then govern in a very significant way the Fermi energy. Yes?
That's why the Fermi energy is at the middle of the graph between the band gap, is because those are the electrons that move between the valence band and the conduction band, and that's why it depends on the free electrons at that level?
Kind of. Just hang with me. We're getting there. Yeah. So the Fermi energy does not vary with the material size, right? It's an intrinsic property that's always a function of the band gap, right? It's always half of the band gap. However, small materials span the same range of energy states as large materials, but with more spacing between the states. Okay, so why is that? It's because if we look at our Fermi energy, our delta E, the spacing between the states is essentially divided by more or less electrons. Okay? And when the system becomes small enough, it's considered discrete or quantum confined. So graphically, what does that look like? If we're dividing the same amount of energy, right, but by different number of states, our delta E becomes smaller and smaller until it eventually becomes continuous, right? So you've probably seen that before, but I wish we had more time to walk through this derivation, but this is where these are coming from, right? Is this notion of the probability of an electron being in a state and the density of states at that point, okay? So how small is small enough? Well, we have to essentially confine an electron or trap an electron. And we talked about it briefly last time that in the purely, if we were being very rigorous about this, it would be the de Broglie wavelength, right? The electron has some kind of wavelength, which is h over the momentum. But that's a really small number, right? The de Broglie wavelength is h over momentum. And if you plug this in, it's like hundreds of picometers, right? Is this right? I think it is. So to confine an electron in that space, where the de Broglie wavelength is the dimensions, or the L is the dimensions of this well, it ends up being a very small number, right? For a single electron, it's hundreds of picometers, which we know from our experience that we can do this with tens of nanometers, okay? The reason is because nanoparticles have a collective wavelength when we start to look at nanomaterials, right? So the wavelength, we tend to think about the wavelength, the de Broglie wavelength is just the wavelength based on the mass of the material, right? But nanoparticles start to have a collective wavelength, which we'll talk about hopefully Wednesday, and that not all electrons participate in that, right? Here we're only looking at the valence electrons, okay? So our confined system doesn't have as many players as you might think it would if we looked at it from a purely empirical kind of approach. So how many conduction electrons would be in a gold particle with 10 atoms? This is to try to make you think about this. So if we had one gold atom for 13, if we had 10, where each of these is representing a valence electron, we would have 10, right? Because if you look at gold, this is 1, 2, 3, 4, 5 S2, 4D9, but we know that that's going to drop there to make that a complete row, so we're left with 5S1. So we have one valence electron per gold. Okay? So if we had a situation, so that's why this is important to remember back how the periodic table works, so you would know how many valence electrons could fall into each of these situations. How many? So if you had something that was, 4D4, you would have 4 valence electrons per atom. Yep.
So the number of valence electrons are in the conduction band. Right? Is that what you're saying? The number of valence electrons of the number?
They can be. They're in the valence band, but they can be excited into the conduction band.
And the other
Yes.
electrons cannot.
Unless you go to really high energy. That's what we were showing here, right? That's why we. So maybe this is the 5s1 of gold, then there's the 4d10 of gold, right? Yeah.
Well, would that mean when you say that the Fermi energy has the number of free electrons? Or depends in terms of this case, where you say that it's like 5s1, so 10
No, we said the Fermi level's constant, but that it's divided by a different number of electrons.
And where does that number?
The number of electrons?
The number of free electrons.
You know it based on knowing the periodic table and the number of atoms in your material. Yeah. Go ahead.
Well, you're saying
Oh, it's
Hold
not
on.
like it's not between like valence or conduction. It's just general, like unpaired electrons.
Yes, valence electrons that start in the valence band and that are the most likely to be promoted into the conduction band. Yeah.
So, question about valence electrons. You said that something with 4 d electrons would have 4 electrons available for this
Yep.
calculation. But based on our example of gold just now, wouldn't something with 4 d electrons abstract an s electron, complete its half shell, and then?
Okay, I picked a bad example. So like 4d2, something like that. Yeah. Is there one back here? Yeah.
So when the electrons are higher than the Fermi energy level, they make their way into the conduction band.
Exactly. Yep. Yep. But at 0K, they should all be in the valence band, the lower. Yeah. Okay. So when we have quantum, yes.
Sorry. So are you saying that n sub e is the number of free electrons, correct?
Where here?
Just in all the equations.
N of E is the number of free electrons.
So aren't the electrons in gold bound to the atoms still? So they're not free until there's enough energy to just think of the atom?
Not when they're. I mean, if you had a single gold atom, yeah, but when you have these clusters of gold atoms, they're very delocalized,
Okay.
right? Yeah, it's not like they belong to one electron anymore.
Oh, so all of this is just calculations for extended solvents
Yes.
based on the dimensions.
Mm-hmm.
Oh, I see. That makes sense.
So it turns out that, do you think it's easier or harder to make a conductor be quantum confined? Harder, right? Because because their conduction and valence bands overlap for one thing, and so, the thing, and so it's harder to confine them into the valence band or the conduction band, right? Because those energy levels overlap, they're much more likely to be continuous, okay? But it turns out that you can, and when it happens, it's at 4 times the Fermi energy over 3 times the number of valence electrons, okay? That's when a metal can become an insulator in one dimension. That's kind of amazing that you can make copper so small that it no longer is a conductor, right? Yeah.
If you follow the same logic when it comes to like silicon, because we're making computer chips and confining the silicon particles possible.
It's a different situation. Quantum confinement in semiconductors is a different expression. So this is a great, maybe I'll put this on the homework because I want to push forward and wrap up semiconductors. But you could do this problem. So silver's a great conductor, but when does silver become quantum confined at 38 degrees C? Knowing that you have the Fermi energy.
Do we need to use KT to somehow get the delta E for this expression? Because our expression just has delta E, Fermi energy, and number of valence. So how do we use it?
So you calculate, it's when does this become less than the KT. This is how much KT is the free energy in the system, right? So you would solve that for when is KT less than for EF3NV. Right?
And NV would basically equal to the number of atoms.
Yeah. Well, no, not for silver.
Silver.
Yeah, I'd have to relook at the periodic table, but yeah, I think you're right. Yeah, because it's directly below gold. Yeah.
Well, if you follow the question, where does size go in these expressions?
Where does what go? Question is, when does that is actually poorly phrased. When does a quantum, I would phrase this as, at what size does a silver particle achieve quantum confinement?
So it's just for one dimension? Assuming it's spherical?
Assuming it's spherical, yeah. I'll put in more descriptors when I put it on the homework. But yeah, so you would see when does this value is better than KT, and then, so then you would know the number of, solve for this, number of valence electrons, and then you could use like the density of silver and Avogadro's number and the expression for a sphere to calculate the size, okay? Quantum confinement in semiconductors is different because here we start to think about an exciton, which is essentially, if I told you I have this thing that has a positive charge in the center and a negative thing floating around it, you would say that's a hydrogen atom, right? And so in this situation, our positive thing is no longer a proton, it's a hole, an electron hole, right? So what this is showing, this is our lattice of all of the material in our semiconductor, and here we've done some kind of excitation to create an electron that has moved in this semiconductor and left a hole, okay? So this electron-hole pair can be thought of as a pseudo-element, not an element, as a pseudo-atom, and people call that an exciton. And an exciton has physical dimensions, just like an atom has physical dimensions, okay? And when we can calculate this exciton radius based on this stuff, which you would be given, materials become semiconductors become quantum confined whenever their dimensions are smaller than an exciton, okay? Yeah?
Are excitons short-lived?
Yes, yes, yes.
How do you measure the mass of the exciton?
It's for our purposes, you would be given it, but it's a function of the mass of the hole and the mass of the electron. Yeah. I made this in graduate school. This is when I first discovered PowerPoint. And I got really crazy with PowerPoint. So this is kind of putting it all together, hopefully. This is a bulk semiconductor. We have conduction band and valence band, right? But as we shrink this smaller, not only does the band gap get bigger, but the distance between these also get bigger, right? Ooh, right? So now when we have this electron, we can excite it. See how it even has a wavelength? It has a wavelength. And we create an electron and a hole, which can be considered an electron-hole pair, which is an exciton. When this drops down, we release, did you notice? It was a different color too. This one was blue. See, that's blue, and then the one that goes off is red. Because it's a longer wavelength, okay? So that's what don't ever spend this much time on PowerPoint. Okay, we'll see you next week.